And as a result, I'm going to present to you something to think about: creating lightning, that is plasma, with a grape. And we'll look at the science behind it as well. First of all, we need a grape. And here we have one. Nice little green grape. It's full of water, and it has a skin, and it has an interesting property. First of all, you could think of it as a little laser where you have two reflective surfaces and an electromagnetic radiation, that is microwaves, that will bounce inside of it. There's something special about this grape, and we have to measure it. And how I'm going to measure it, I've come with a ruler, and I placed the grape beside the ruler. And I've also, wanting to get really precise about it, looking at a distance from 20 centimeters to 24 centimeters, I could calculate that that's 40 millimeters. And if you measure how many pixels that is, 1812.9 pixels divided by 40 millimeters, we get 45.3 pixels per millimeter. This is important because we need to know what the size of this grape is. Measuring the grape, I have 1664.5 pixels, which equates to 36.7 millimeters, an important number. And we'll find out later why that's important. The equation that we're going to use to determine frequency is equal to the velocity divided by the wavelength. I want to know what the wavelength is going to be, so that's going to be velocity divided by the frequency is going to give me the wavelength. In our case, the velocity here is the speed of light, which is in meters per second. I'm using a microwave that is 2.45 gigahertz, and as a result of that, I could get a wavelength of 0.122 meters, or 122.364 millimeters. As I said before, it is important to recognize what type of grape I'm going to be using. In this case, you're going to see that the total number of wavelengths is equal to the width of the grape divided by the wavelength of the microwave energy. In this case, it's equal to 0.3001 lambda. Now, interesting enough, this is a very important aspect of the grape, because you see, if you use any grape, you're not going to necessarily get what I'm going to show you, which is lightning. See, this grape is really a dipole antenna with a length between 0.25 and 0.3 wavelengths. This is matched in order to allow for something that is going to give me harmonics, or a standing wave. In this case, you'll see that the third harmonic, 3F, or 3 times the frequency, is 7.62 gigahertz. Well, lo and behold, lambda 3, which is equal to the velocity divided by bracket 3 times the frequency, equals 0.039 meters, or 39.34 millimeters. Very close to the harmonic frequency that I'm looking for within the grape. Thus, 36.725 divided by 39.343 times 100% is 93.4% fit of a third harmonic. This is important because without it, you're not going to see the plasma. You see, we have to fall within that wavelength pattern, 0.25 to 0.3 wavelengths. I'll show you what I mean. Here we have the grapes. I'm going to set the time to 1 minute, and we're going to fire it off and see what happens. As you can see, the grapes are going around in circles. And nothing happens. Why is that the case? Well, in this case, these two grapes that I'm using don't meet the picture that I showed you. But given the right circumstances, we will see that these two grapes in particular will give us the results that we're looking for. Set it for 1 minute, fire it off. There you go. Isn't that cool? So, what did we learn from this experiment? We learned that two grapes that are close together, that meet the requirements of specific harmonics, will create lightning in your microwave oven. There's a lot more that I could say about this, like measuring how many gigahertz is in the microwave oven, or the measure exactly the precision of the grape itself based on the time it takes to ignite. But I'll leave that for another story. Have a great day.